start. Anybody have any questions on homework?
Is there an easier way to figure out the rule of thumb they've got there? Other than if you're doing it manually, trying to average everything out and compute it?
Oh, okay, so basically they give you a probability distribution and ask for, a suitable range.
So what it says at the beginning is like, use the rule of thumb to figure out this, they give you your table, and then you understand that you have to have your average and computation, 2 times whatever that is going to actually be. It took me a minute to figure that one out, but it's just, I wanted to know if there was a simple way to figure that one out.
Yeah, so basically you need to find the mean and you need to find the standard deviation so that you get the mean plus or minus 2 times the standard deviations. And so that's given that you have a probability distribution that's given to you. And so we talked about the formula to manually find the mean and the standard deviation, but also on the calculator you just enter in the 2 columns.
That's what I ended up doing, I mean, you just have to make sure that, that the column actually equals 1, because otherwise everything after that is gonna be, you don't have a probability distribution, so. So I gotta figure that part out, it's just like that I missed a key part here about the quicker way of doing that.
So the key thing is that any probability, any distribution, whether it's a probability distribution or not, you can find the mean and standard deviation. Just if it's a probability distribution, there's a special formula for it because the second column adds up to 1. But if the second column doesn't add up to 1, it's still a type of distribution, maybe not a probability distribution. But you can still find the mean and standard deviation in the same way. Any other questions? Okay, let's move forward. So, last time we talked about binomial probabilities. So let's review what we talked about. So we said a binomial probability was when you had a probability of a situation that had a certain structure, like the probability of a number of successes out of another number of trials. And there's this implied word here, which is exactly that many successes. Then in this case, also as long as the assumptions are met, then there's a formula associated with it, which is this formula we talked about last time. And really there's just these 3 individual components. One component has to do with the successes, one component has to do with the non-successes, one component has to do with the number of ways you can have that many successes and non-successes. So, we said, so an example, or examples, is, let's say that you flip a third coin 10 times. Let's say you want to find the probability of exactly 8 heads out of 10 flips. We said that this ends up being a binomial probability. The reason for that is because it fits the structure that we've been talking about, which is the probability of exactly some number of successes out of another number of trials. And so you can just use this formula. So the first part would be n choose x. What would that be here?
10 choose 8.
Yeah, 10 choose 8. Times p here we defined as the probability of success per trial. So success in this case would be heads. So what's the probability of success for a third?
1/2.
Yeah, 1/2. And then raise the number of successes we want. Yeah, which in this case, this would be x, which is 8. And then times the probability of non-success, which is tails. And the formula is 1 minus p, so it would be 1 minus 1/2, which is 1/2, which is the probability of tails for a fair coin, which is what we expect. Raise the number of non-successes or tails, 2. So this would be the probability of exactly 8 heads for a fair coin. Okay. So that was an example. So last time we also talked about what assumptions must be true. So the fine print. So what assumptions did we say have to be true?
Two outcomes per trial.
Okay, good, 2 outcomes per trial. And generically, we call those outcomes success or non-success. So per trial or per coin flip in this case, there are only 2 outcomes. They're either heads or tails. There's nothing else that you could possibly observe that you care about for a coin flip. So last time we also mentioned the important distinction that we say that there are 2 outcomes per trial that you care about. That doesn't mean that there have to be 2 outcomes total. It's just 2 outcomes that you care about that you can distinctly label as success, and everything left over is non-success. So example, we talked about how if you roll a fair die, that normally there would be 6 outcomes, 6 faces that you could probably, that the die would land on. So there's 6 outcomes there, but if I were to ask you what's the probability that you roll it 10 times and you observe 2 sixes, then let's see. So let's do both cases. So if I say roll a fair die, and I ask you what's the probability, roll a fair die 10 times, and I ask you what's the probability you'll get 2 sixes, 3 ones, and 1, 2. So these should have it at the time. So 5, 6. So you roll a fair die 10 times, and you want the probability that of those 10 times, you're going to observe 2 outcomes that are sixes, 3 outcomes that are ones on the die, and 5 outcomes that are twos. So question is, would this be binomial? Would you be able to use the binomial probability formula? No, because there's not just 2 outcomes per trial that you're keeping track of. For each roll of the die, you're keeping track of whether it's a 6, a 1, or a 2. So there's 3 outcomes per trial here. We talked about how this is multinomial or specifically trinomial, and you would not be responsible for this in this class. So if this question that was asked for you, you would just say this is not binomial, and that would be it. But if I change the question where I ask what's the probability that you get 2 sixes, and 4 and 8 non-sixes, would this be binomial? We could use that formula.
Yes.
Yeah, very good. So because each time you roll it, you're only keeping track of whether it's a 6 or whether it's not a 6, a success or non-success. So in this case, there's 2 outcomes per trial. So, this one would be not binomial. We cannot use that binomial probability formula. And this one would be binomial. So keep in mind that this assumption, 2 outcomes per trial, is part of why it has this name of being binomial, bi means 2. But keep in mind that just because there are 2 outcomes per trial, doesn't mean that you can use this formula. It's necessary but not sufficient. So there's another assumption that needs to be true, and also it has to fit this structure of being the probability of a number of successes out of a number of trials. So what is the other assumption that we talked about?
Each trial has to be independent from the
Very
other.
good. Each trial is independent. So what that means is that if you end up having a success, if you end up observing a success, does that change the probability of observing a success again in the future? If it doesn't change the probability, if the probability is consistently the same for success, then we call that independence. If you observing a success ends up changing the probability of success later on, then those trials are not independent. And the significance of that is the probabilities end up changing. There are different values for the probability of success. And so you will not be able to use this formula because this probability of success ends up being a different number every time and not the same number that you can just raise to a power. So you need each trial to be independent for you to be able to use this formula with accuracy. So in this example, we had trials that were independent. And so let's look at this case where we said we could use the binomial probability formula. So if we want the probability that you roll 2 6s and 8 non-6s, then again, there's success and non-success, so 2 outcomes per trial. But also the trials are independent, because if you roll a 6 on one roll, what's the probability of that roll being a 6?
1 out of 6.
Yeah, 1 out of 6. So then the question is, if you were to roll a 6 one time, later on, what's the probability of rolling another 6? Is it still 1 out of 6? If it is still the same, 1 out of 6, then we say the trials are independent, because we're able to use the same probability of success over and over again. Any questions? Okay, so these are the 2 assumptions we said have to be true, as well as the situation having this structure, so that you could use the binomial probability formula with accuracy. So that was our review from last time. Anybody have any questions?
So punching that one in, it would be 1 6 squared multiplied by 1 6 to the 8th. Instead of trying to do 2 6 and 8 6, right? Because it's the probability to the power of how many you're trying to get.
Which one did you just do?
The bottom one you were talking about when it was the 2, right? When you had 2 6s and 8 non-6s.
Oh, okay.
So it'd be 1 6 squared,
Yeah, it'd be 1 6 squared.
and then
5 6.
1 6, or yeah, 5 6 to the 8th,
Yeah.
right?
And then the 10 choose 2. Okay, good. So let's continue. Today we'll talk about, last time we talked about a binomial probability. Today we'll talk about a binomial probability distribution. So sometimes the word probability is left out, so that it's just called a binomial distribution. So this idea of a binomial probability distribution or a binomial distribution is a combination of the concepts, the last 2 concepts that we talked about. So a binomial probability distribution is a probability distribution, where all probabilities are a binomial. So let's look at an example of that. So let's go back to the case of flipping a fair coin 10 times. So let's say that you flip a fair coin 10 times. And the first exercise is, let's construct a probability distribution. You remember a probability distribution you can represent as a table with two columns. One is all values of a certain variable x that you're keeping track of, and then the other column is the probability of each of those values. So we want to construct a probability distribution where your x variable here represents the number of heads observed out of 10 flips. So basically, a probability distribution can be represented as this table of two columns, where one column is your variable of interest. In this case, the variable of interest is told to you to specify or represent the number of heads observed out of 10 flips. So x here is number of heads out of 10 flips. So recall that in any distribution, much less a probability distribution, in your column representing the values of your variable, you want to list out all possible values of that variable. So if a variable here represents the number of heads out of 10 flips, then what are all the values that that variable can take?
0 to
0
10.
through 10.
0 through 10, very good. So either you observe no heads after you flip the coin 10 times, or the maximum number of heads you could observe is 10, and then there's everything in between. So these are all the possible values representing the number of heads that you could observe after flipping a fair coin 10 times. And so in a probability distribution, we also want to list the probabilities of each value. So how do you find the probability that you'll observe no heads out of 10 flips?
Use the binomial probability formula.
Okay, good. So use the binomial probability formula that we just talked about, because each of these is a probability of a certain number of successes out of another number of trials. And x is each particular number here, and n is 10. So to find the first probability of 0 heads out of 10 flips, use the binomial probability formula. So let's do it together. So the first term would be n choose x, which would be what in this case?
10 choose 0.
Yeah, so we're going to be careful. So 10 choose 0 is the first one. But if you just plug in 10 choose 0, what do you get? So, we wanna be careful here because this ends up being one, not zero. And so then we would multiply by p to the x, so this is a fair coin, p the probability of heads is 1/2. Raised to the number of heads,
Which would be 0.
which is 0, so anything raised to 0 is gonna be 1. And then 1/2 raised to the number of tails,
Which would be 10.
10. So you have three terms here, just like before, when we've been using the binomial probability formula. But some of these terms can be, end up being simplified. So 10 choose 0 simplifies to just 1. And then 1/2 to the 0 simplifies to just 1. So you have 1 times 1 times 1/2 to the 10th. So the answer here is just gonna be 1/2 to the 10th. And 2 out of the 3 terms just get wiped out to 1.
I don't understand how it's 1/2.
Oh, because you have a fair coin here, and using our formula, P is the probability of success per trial. So success, because we're finding the probability of 0 heads out of 10 flips, heads would represent our successes. So because we have a fair coin, the probability of success or heads for a fair coin is 1/2. So that's why anytime you see P here, in our example, we're gonna use 1/2. And then 1 minus P is 1 minus 1/2, which is 1/2.
Right.
Yeah. Okay, so the point is, the answer to the probability of 0 heads out of 10 flips means that you get all tails, and the answer to that is 1/2 to the 10th. Now, we got that using this binomial probability formula, but recall that you could have gotten this answer before on test 1. So this is actually what we covered before on the unit on test 1 in chapter 4. So you were able to answer this question without the stuff on chapter 5, binomial probability formula. And the reason for that is because getting 0 heads out of 10 flips is another way of saying you get all tails. Right, that means the first flip is tails, and the second flip is tails, and the third flip is tails, and so forth. So probability with and is multiplication rule. So we can just multiply the probability of tails all 10 times, and that's what this is. So you can either get this answer by what we talked about in chapter 4, which is multiplication rule, or you can get it this new way by using the binomial probability formula. Same result. Okay, any questions? Okay, so that's the probability of 0 heads out of 10 flips. How would you find the probability of 2 heads? I do 2 because it's not enough room here to do the 1, so we'll just do 2.
When you lose a 0, you put a 2 in because the first 1/2 is put to 0 here, and the second one is put to 10. You'll change that to the first 1/2 will be put to 2, the second one put to 8.
Okay, very good. So basically, we're gonna use the same binomial probability formula, but instead of 0 successes, we're gonna have 2 successes. And instead of 10 tails or 10 non-successes, we'll have 8 tails. So this is the resulting formula. So it turns out that in this probability distribution, where we're listing the probabilities for all these possible values, that the way we find all the probabilities from 0 to 10 is that we're gonna use this binomial probability formula in all cases from 0 to 10, all 11 cases. All right, so these end up being all binomial. So all the probabilities here of all these values in the distribution were calculated using the binomial probability formula. So because that's the case, we call this probability distribution a binomial probability distribution. So a binomial probability distribution is when a probability distribution represented with 2 columns, x, p of x, where all probabilities are binomial probabilities, calculated using this formula. Any questions? Okay, so once we recognize that we have a binomial probability distribution, which is a special case of a probability distribution, let's talk about the mean and the standard deviation. So let's talk about mean intuitively. So finding the mean of this distribution means that if you're looking at multiple instances of this variable, for example, this variable represents the number of heads you end up observing out of 10 coin flips of a fair coin. So let's say that you flip this fair coin 10 times, and then you count the number of heads you just observed. And so let's say that of those 10 times, you happen to observe 6 heads. And then you flip the fair coin 10 times again, and then you observe 5 heads. You flip the fair coin again 10 times, you observe 4 heads, and so on. Let's say you repeat this process, flipping the fair coin 10 times, a number of times that approaches infinity, like 1,000,000 times. So you have 1,000,000 numbers, where each number represents the number of heads you observed out of 10 flips of a fair coin. So if you were to take the average of all these 1,000,000 numbers representing the number of heads you observed out of 10 flips, then what do you think the mean should be?
1/2 raised to the million.
So remember, each of these numbers represents the number of heads you observed in a fair coin, which can only go from 0 to 10. So the number of heads is what each number here represents. So if you repeat this process 1,000,000 times, where you're flipping a fair coin 10 times and recording the number of heads, and you have 1,000,000 instances of that, then if you take the average of all these numbers, which can only range from 0 to 10, then what should the average of all these numbers be?
It should be the number of trials times the probability of each trial.
Yeah, so you already know that this is a fair coin, and you're flipping it 10 times and observing the number of heads each time. So in a fair coin, if you're only flipping it 10 times, then even if it's perfectly fair, you're not guaranteed to observe exactly 50% heads, right? One time you could observe 60% heads, another time you could observe 40% heads, and so forth. But in the long run, if you repeat this and you take the average of all of them, how many number of heads should you expect to observe out of 10? 5, because it's a fair coin, very good. So if you take the average of all of these, if you add these all up, all the 1,000,000 numbers, and divide by 1,000,000, you should get 5. And that's what we mean by the mean of this probability distribution. So the mean of this probability distribution should be exactly 5. But keep in mind that we also talked about how to find the mean of a probability distribution, which is the first thing we talked about in chapter 5, like 2 classes ago. And so recall, if we have any arbitrary probability distribution, for example, we talked about numbers in a hat, for example, where each one had a probability associated with it. How do we find this mean?
It's the sum of each x times the probability.
Okay, very good. So the sum of the product of each x times p of x. So find each product of each row and then add them all up. And remember the generalized formula is this: the sum of all x times p of x. So this applies to any probability distribution. And a binomial probability distribution is just a specific case of a probability distribution. So this way to find the mean works for any probability distribution, including binomial probability distributions. So it turns out that to find this mean, you could also do this. You could find the product of each row and then add them all up. However, we were able to find the mean and know that it was 5 without having to do all that. So if it was a binomial probability distribution, how do you think we can quickly find the mean instead of having to add up the product of all the rows? How do we get this 5 so quickly?
You multiply the number of n trials times probability.
Yeah, we multiply the probability of heads for a fair coin for each flip, which is 1/2. We multiply by the number of trials, which is 10. So 1/2 times 10, that's how we're getting the 5. So that turns out that if you have any binomial probability distribution, where all the probabilities are binomial probabilities, then to find the mean, you can use this easy shortcut, which is simply n times p. So the mean of any binomial probability distribution is simply n times p. And that'll give you exactly the same answer had you used the general formula for the mean to find the mean for any probability distribution. Find the sum of the products of the rows. If you did all this work, you would get exactly 5 as well. Any questions? Yeah.
So here, this fair coin, the probability is the same all the way down for both success and non-success.
Mhm.
It's 50%. What if we're dealing with a situation in which that probability is not the same all the way through for both success and non-success?
Okay, so good question. It turns out that exactly the same situation where to find the mean of that particular binomial distribution, still the same formula.
So is it?
Yep.
Okay.
And we'll see an example of that in the next thing we do. Questions? So any binomial probability distribution, or all the probabilities are binomial probabilities, to find the mean, it's simply n times p. So let's do another example while the question is fresh. So the question is, in this case, the probability of success and non-success, heads or tails, is the same. So it seems like that would be kind of coincidental and affect whether this formula works or not. And so let's see an example now where the probability of success and non-success are actually different and see whether the formula works. So let's say that you had a multiple choice test, 32 questions. And you had 4 choices per question. And so the question is, if you were to randomly guess on all 32 questions, and you were to repeat this, or you had 100 million different students in the country guess on a 32 question multiple choice test, and you took the average of all their scores, what would the average be if all of them guessed on all 32 questions?
Relatively low.
Okay, so let's quantify that. So again, so you can think of this as your x variable here is you're keeping track. So you're trying to find the mean number of questions that students are getting right by guessing out of 32 questions. So you're trying to find the mean number correct out of 32 questions. So this quantity that you're trying to find the mean of, that's our variable of interest. That's what we can call x in our probability distribution. So x here represents the quantity you're trying to find the mean of, which is the number of questions correct out of 32. So you imagine mentally constructing this probability distribution where x represents the number of questions correct out of 32. And so, just as an exercise, what are all the possible values? 0 to 32. Okay. Either they get not a single question right, or they could get all 32 questions right by guessing, or anything in between. So those are all the possibilities. So then if you look at the probability of that variable taking on all its values, how would you find the probability of each of these? which is the probability of a number of successes out of another number of trials. How did you find the probability of each of these instances? Yeah, you use the binomial probability formula because it's the probability of exactly a number of successes, a number of questions correct, out of 32 questions. So these would all be binomial probabilities. And because you're dealing with a probability distribution where all probabilities are binomial probabilities, we have a special case of a probability distribution called a binomial probability distribution. And if you have a binomial probability distribution, then to find the mean, you can use this shortcut where the mean value of this variable in that binomial distribution is n times p. So what's n in this case and what's p?
N is 32, and
Okay.
P is 1/4.
Okay, good. So you look at each binomial probability, where it's the probability of a number of successes. So success means getting a question correct. And n, the total number of trials, is 32. So then n is 32. P would be the probability of a success, which in this case is getting a question correct. And that's going to be 1/4. There's 4 choices per question. So 32 times 1/4, that's going to be 8. So that's telling you that because every one question that you guess on, you get a 1 in 4 chance of getting it right. If you have 32 questions, then in the long run, you're going to get, on average, 1/4 of the 32 questions right, which is 8. So if you have 100 million students in the country guessing on a 32 question multiple choice test, and then you look at all their scores at the end, the average will end up being exactly 8.
It's that simple.
Yep, it's that simple. But the hard part is recognizing that the situation is a binomial probability distribution where all these probabilities are binomial. And only in that case can you use this formula in times p. So only in the special case when the probability distribution is binomial. Any questions? So let's compare that case to the very first example we did in chapter 5, which is when we talked about a general probability distribution and not necessarily a binomial probability distribution. In that case, we said, okay, you have numbers in a hat where each number is weighted a certain way. And if you're asked to find the mean, then you couldn't use the shortcut of n times p, because this is not a binomial probability distribution. These probabilities were not calculated from this formula. They were just arbitrary probabilities that were given to you for each of these numbers. And so in that case, you have to use the general formula to find the mean for a probability distribution, and not the special formula that applies only to binomial probability distributions. Any questions? All right, so now that we talked about what a binomial probability distribution is, where all the probabilities are binomial, we talked about, in that special case, the mean has a special formula, and it turns out that the standard deviation also has a special formula. So if you have a binomial probability distribution, then the mean is n times p, and the standard deviation is simply the square root of n times p times q, where q is defined as 1 minus p. So q is just a complement.
so then the variance would just be n times p times q.
Very good. So the variance is always the square of the standard deviation. So in this case, the variance would be the square of the square root of NPQ, which is just NPQ. Okay, so let's do an example. So let's continue with this example of this 32 question multiple choice test. And recall that you learned from your homework when they were asking you questions on the range rule of thumb. Basically, so the mean tells you what the most typical score is if you were to guess on all 32 questions. So the most typical score you can expect to see is 8 questions correct out of 32 questions. But does that mean that every time you guess on a 32 question multiple choice test, you should be saying 8 questions correct? No, it's just the most typical number or the average number. So that brings us to the next question, which is, what is the typical range for the number of questions you should expect to get correct out of 32 questions every time you guess on that test? So what is the typical range of the number of questions correct out of 32? I guess. So recall from your homework, where they keep calling it the range rule of thumb, that we say that, okay, let's forget about the range rule of thumb for now, and I'll come back to it. But in statistics, when we say the values are typical, so typical values are values within 95% of the mean. So anytime you have any distribution, regardless of the shape, let's say that distribution has this funky shape. So let's say the mean happens to be here. So all values within 95% around that mean are considered typical. So around 95%, so that only 5% in both the low and high end are left over, then these are considered typical values. And that's for any distribution. So just convention is that typical values are defined as being 95% within the mean for any distribution. But let's say we specifically have a bell curve. We also call that a normal distribution. So if we have a bell curve, and we've talked about how there's a relationship between the percent of the values and the number of standard deviations in that range. So 95% in a bell curve is within how many standard deviations?
2.
Yeah, 2 standard deviations. So the mean, plus or minus 2 standard deviations for a bell curve, constitutes 95%. And your book uses the phrase range rule of thumb to say that the mean plus or minus 2 standard deviation is a quick way to approximate all values that are considered typical, regardless of whether it's a bell curve or not. Because in the range rule of thumb, you're just assuming it's a bell curve, whether you know that's true or not. But it's just, that's why it's just a rule of thumb. But, so, in this case, let's use that range rule of thumb to find all values that are considered typical, i.e. the mean plus or minus 2 standard deviations. So we need to know the mean, and we need to know, what one standard deviation is. So this is a binomial probability distribution, so we said that the mean and standard deviation have shortcuts. So the mean will be n times p, in this case that's 8. And let's calculate the value of one standard deviation. So let's plug in the numbers, what's n?
It's 32.
32.
Yeah, n is 32.
Use 1/4.
Yeah, p is 1/4.
And Q is 3/4.
Q is 2/4. So if you just multiply all these numbers and then take the square root, let me know what you think.
$2.449.
2.449.
So let's approximate that just for ease of calculation, say it's 2.5. So it's 2.5 times 2. So then we're saying that all range of typical values are the mean plus or minus 2 standard deviation, which in this case is 8 plus or minus 5. So 8 plus or minus 5 means you're getting a range where the low end is what? Is 3, and the high end is, yeah, so it's gonna be 8 plus 5, which is 13. So you're getting this range, the values between 3 and 13. So what does that mean? That means that every time you guess on a 32 question multiple choice test, you should expect to get the number of questions right that corresponds to values in this range. Anywhere between 3 questions and 13 questions right, every time you guess. So if you guess, you don't know what you're doing, so why is there this lower bound here set of 3? Why don't you think that it would be 0? If you didn't know anything, why wouldn't it be typical that you get 0 questions right?
I mean, if you're guessing just purely by random chance, you always have a 4 if it's not 0%.
Yeah, very good. So even if you don't know anything, if you're guessing on a multiple choice test, then you still have a 1/4 chance of getting it right, just blind by. So because of that, if you're actually randomly guessing, then it's very unlikely that you'll get 0 correct, or even 1 or even 2. You'll get at least 3 correct by guessing on a 32 question test. Any questions? So, if I were to give you a multiple choice test of 32 questions, and let's say that your score ended up coming back as somewhere between 3 and 13, what do you think can be assumed?
The class did badly.
Well, one particular student then, not just the whole class, but if one particular student gets a score that's between 3 and 13,
They just guessed on it,
yeah, so you can probably assume that either they guessed on all the questions, or they have the same knowledge as somebody who guessed. Any questions?
I feel like the guy you need to tell that to is here right now. Class plans laid out, delivered. Where's your mic?
All right, any questions, guys, comments? All right. So now, given a scenario, you should be comfortable recognizing whether it's a binomial probability distribution or not.
Thank you. That was a funny statement.
Okay, let's practice that then.
Couldn't hurt.
It's like, Could you do the work? Probably. Could you recognize it? Now, that's a different challenge.
Okay, okay, good. So let's say that in a certain country, let's say you find that the probability of having a girl is, let's say, 0.52. And you want to know that if you're observing a sample of 10 children, and let's say you observe lots of samples of 10 children, and you count the number of girls in each samples, what would the average number of girls be in the sample of 10 children? So the first question is, what's the average? It is.
That would be 5, because you have n minus 10, p is 0.52. Technically it's 5.2, but that was around 5, so.
Okay, very good. So the hardest thing here is just to recognize that we're dealing with this concept of a binomial probability distribution. And so you're not expected to immediately realize that that's the concept we're dealing with. So it's going to take a logical progression to conclude that this is actually this concept. So the progression would be that you're trying to find the average of this quantity, the number of girls in a sample of 10. So that thing that you're trying to find the average for, we talked about how to find the average value of a variable in a general probability distribution, as well as the average in a specific binomial probability distribution. So the first thing you have to decide is whether this x variable, the number of girls in a sample of 10, is just any arbitrary probability distribution, or is it specifically a binomial probability distribution? So to build up to that, ask yourself, if you were to construct the probability distribution, where x is this quantity, the number of girls in a sample of 10, first of all, this probability distribution, the first column, we need to list out all possible values of this variable. So what are all the possible values?
0 through 10.
0 through 10. And then you ask yourself, how do you find each of the probabilities? If all the probabilities can be found using the binomial probability formula, then all these probabilities are binomial, and hence this entire probability distribution is a binomial probability distribution. And then you can use the shortcut formulas to find the mean and standard deviation. So, is that the case? Can you use the binomial probability formulas for all these probabilities?
Yeah.
Yeah, and the reason is that all of these probabilities are the probability of exactly a number of successes out of another number of trials. Specifically, it's the probability of exactly either 0 or 1 or 2 successes, and so on. Successes out of 10 trials. And so it fits the structure of a binomial probability formula, and not only that, it matches the fine print of the 2 assumptions we talked about. So 2 outcomes per trial. So for each trial or each kid, you can only be one of 2. And the second assumption is also true, is that they're independent. So you're assuming that if you end up observing a girl in one instance, that it doesn't change the probability that you'll observe a girl again later. So the probability will consistently be 0.52. So because of that, we can use the binomial probability formula, calculate all these probabilities. In which case, because all these probabilities are binomial, then the entire distribution is a binomial probability distribution. And then to find the mean, it's simply n times p. So this is an example of actually getting the answer is easy, but realizing that you need to use this formula is actually the hard part. So in this case, n times p, what's n and what's p?
N is 10 and P is 0.52.
Yeah, and it's 10 and p is 0.52. So this would end up being 5.2. So if you took the average of all observations of 10 children and observed the number of girls, the average will be 5.2. Any questions?
So if we were trying to find the standard deviation, you'd be, MPQ would be 10, 0.52, and then 0.48.
Yeah, okay, so standard deviation would be the square root of NPQ.
I didn't do square root, there's the problem. Thank you.
That would be the square root of 10 times 0.52 times 0.48. Okay, questions? All right, so given a situation, you should be comfortable determining whether it's a binomial distribution or not. If all the probabilities are binomial, then the distribution is binomial. And then if it's binomial, then you should be comfortable finding the mean and standard deviation. It's just a simple formula for each. You guys have any questions? Okay, so we actually have some bit of time left. So what we'll do is, we actually covered all the material we were planning to today. And so we're gonna go ahead a little bit and start what we're gonna talk about tomorrow. So, so then that way we have an opportunity to talk about multiple concepts multiple times, and it'll just reinforce everything.
Random question, because it was in some of the program for my math lab. Are we gonna be covering the Poisson probability
No,
distribution?
no. So we're skipping the chapter on Poisson distributions, and we're just doing binomial probability distributions. If you get inspired to do stats 2 later on, then that class will cover the Poisson distributions. So we're gonna start chapter 6. Chapter 6 will be on normal distributions. So a normal distribution is just another word for bell curve. It turns out the bell curves are used so often in real life by people of all different fields that people in different fields have adopted different terminologies for the same idea. So other people also called a bell curve a Gaussian distribution. So these are all words meaning the same thing. So earlier in the semester, we talked about a bell curve. We started introducing it. So recall that a bell curve is a distribution where you're looking at, on the x-axis, values of a certain variable. Let's just say x. And then on the y-axis, you're looking at how often that value occurs. Let's say p of x. And the bell curve has a distribution that's a bell shape, where there's some value of x here that has the most representation, has the highest probability. And as you move away from that value of x, you have less and less representation, the further away you are from the mean. So an example is, let's say we look at weights of men. I'm gonna leave women out of this weights. And let's say that you go out and you measure a whole bunch of men in the population, you measure their weights, and you punch all those weight numbers in your calculator. Calculator tells you the mean is 180, and the standard deviation is 20 times. So when we first started talking about bell curves, we talked about how there was a relationship between the percentage of the population that lie within a certain number of standard deviations from the mean. So we said that within one standard deviation of the mean
Was 68%.
was 68% very good. So 68% of all men are within one standard deviation of the mean. So what are the range of weights that are within one standard deviation of the mean?
160 and 200.
Yeah, 160 to 200.
Next one's gonna be 140 and 220, that'll be 95%.
Okay, excellent.
And the next
So-
one will be 240 and 120 at 99.7.
Okay, very good. So let me just use these two examples. So within two standard deviations, all values in that range constitute 95% of the population, and so forth. So any fixed number of standard deviations from the mean, you have this fixed relationship. So this is all well and good. If I were to ask you what percent of all men have weights that are between 160 to 200, you would know that it's 68%. But I would have to ask you a range of values that were around the mean and the same distance around the mean. If I asked you for what percent of all men have weights between 215 and 230, for example, these values are not centered around the mean, and therefore, based on what we've already talked about, you would not be able to answer this question. So what percent of all men have weights between 215 and 230? Because these values are not centered around the mean of 180. They're not a fixed number of standard deviations from the mean. Based on what we talked about, you wouldn't be able to answer this question. Okay, any questions? So let's talk about how we can actually answer this question. If you're given an arbitrary range representing values, and they weren't necessarily centered around the mean, how would we find the percentage of values in that range? Okay. So let's say that we're trying to find the probability that a man's weight was less than 215 pounds. So let's say that you have this bell curve of weights, and 180 is here, and 215 is here. Okay, so it turns out that this bell curve has a very specific mathematical relationship. You can describe it exactly with a function. And it turns out that later, if you guys decide to take calculus, you'll learn that you can find the area under any function using a certain operation in calculus called the integral. And you can find the area under any shape, any function. So in this case, so because this is has a mathematical function associated with it, it turns out that using calculus, we can determine that the total area under the bell curve, if we were to extend the left and right to negative infinity and positive infinity, if we were to extend both ends indefinitely and find the total area under the bell curve, that area ends up being exactly 1. And that turns out to be very convenient, because if the total area under the bell curve is 1, and the total probability of all possible values, has to be 100% or 1, then now we can have an equivalence between area under the bell curve and probability between two values under the bell curve. So now we can make an equivalence between area and probability. So if we want to find the probability that this weight variable is less than 215 pounds, then we look at 215 pounds here, and instead of probability, now we know that there's an equivalence between probability and area under the bell curve. So we can convert this probability question into an area question. And you might be thinking, well, that's great, but area sounds harder than finding probability. So it turns out that you can find this area easily using calculus. We don't expect you to know calculus in this class. So what's done is that there's a table where people have filled in the table using calculus, and all you have to do is, there's a table where there's a relationship between a z-score for a data point and the area under the bell curve to the left of that z-score. So there's a table where there's a relationship between z-score and area to the left of that z-score under the bell curve. So if we want to find this area to the left under the bell curve of this data point of 215, all we need to do to use this table is to know the z-score of 215. And once we know the z-score, we can use the table to find the area to the left of that z-score under the bell curve. So we talked about z-score in the past. How do we find the z-score of 215? And what does the z-score even mean? You guys remember?
The z-score is x minus the mean divided by the standard deviation.
Okay, excellent. So recall that the z-score of a data point is the number of standard deviations that data point is away from the mean. So we know that this data point is 215 minus 180 pounds away from the mean. And if there are 20 pounds for each one standard deviation, then to find the number of standard deviations, we divide this absolute distance by the number of pounds for each one standard deviation. So this will give us the z-score. So if we calculate this, we can get 35 over 20. looks like 1 1/3. No, 1
1 3/4.
3/4, thanks. So that's the z-score. So all we need to do now is use the table, which gives us a relationship between z-score and the area to the left under the bell curve. So we're gonna look up 1.75, and then we'll see in the table what area corresponds to that. So we're gonna practice using the table together. So this z-score table is probably the most used table in the book. So it's located in multiple places. So one place that you can find it is the very last cover in the back cover. You'll see tables that say negative z-score or positive z-score. It's also found in the middle insert, this kind of thick cardboard portion of the book. This insert, you'll also see it says negative z-score, positive z-score. And then besides that, there's an appendix of all possible tables, and that's, it's also located there. Appendix, so appendix A, also negative, positive z-scores. So 3 different places in the book. So let me just use them on the back. So first of all, what you'll notice is you'll see that this table is divided into negative z-scores and positive z-scores. And when we calculated our z-score, we got a positive number. It was positive 1.75 when we calculated the z-score in the formula. But let's talk about the first thing, which is when would you have a negative z-score for your data point versus a positive z-score?
You'd have a negative z-score if the value is less than the mean.
Yeah, very good. So remember, if you have a certain data point, like in our case we had a data point of 215, any z-score calculates the number of standard deviations you are away from the mean, but it's also assigned distance. So if our data point is to the right of the mean, then we're gonna have a positive z-score. If our data point is to the left of the mean, like 110, then we'll have a negative z-score. What if our data point is exactly the same values as the mean? What's our z-score? 0, very good. So because our z-score that we calculated is 1.75, we're going to use the positive z-score side. And then the first column here of the table lists the z-scores, and all these middle numbers here in the table represent the areas to the left of that z-score under the bell curve. So first column is z-score, all the middle numbers represent areas. So we're going to look for 1.75. So they're in order, so 1.7 is here, and then we want an extra 0.05. So in the table, if you add in each of these little bits, you're adding in this extra amount. So we want to add in an extra 0.05. So we start with 1.7, add in 1.05, so that would be here. So then we go down the 0.05 column until we meet the 1.7 column. So 1.7 is here. So then our z-score will be 0.9599. Or the left area of that z-score will be 0.9599. Any questions? So particularly for this particular z-score of 1.75, the area in the table is 0.9599.
So then multiply it by 100 for your percentage and you're done.
Yep, if you want to, but by convention, any probability is from 0 to 1, so this already represents a probability. But if you wanted to express it as a percentage, then you'd multiply by 100, and that would be correct. Okay, so this number in the table, what it represents is the area to the left of the z-score. So notice that every data point, like 250 in this case, will have a z-score, in this case 1.75. And that data point, which has that particular z-score, has an area to the left and it has an area to the right under the z-score. The table, the z-score table, will by convention give you an area to the left. What if you had wanted an area to the right instead?
Could you take 1 minus the area to the left?
Very good, because we've said that the total area under the bell curve ends up being exactly 1. So if you want the area to the right, you would take the total area, which is 1, and subtract this left area, and that would give you a right area. So this left area is 0.9599, and therefore the right area will be 1 minus that. Yeah, so it'd be 0.0401. Okay, so to answer this first question, what's the probability that a man's weight will be less than 215 pounds? That will be equivalent to finding an area to the left, because the probability of the variable being less than is the same as the area to the left under the distribution. So this left area, using the chart, after we find the z-score, using this formula of 1.75, then the chart will give us a left area of 0.9599, and that left area will be equivalent to this probability of being less than. So the answer to this question is 0.9599. So 95.99% of all men have a weight that's less than 215 pounds. Any questions? Okay, the next related question is, what if we wanted the probability of a weight being greater than 215 pounds?
We answered that.
Yeah, we answered that. So in that case, greater than is equivalent to finding the area to the right under the bell curve for that data point. So the area to the right means that if we hadn't just done that, then you would have to go through the motions of finding the z-score, using the chart to find the left area. From that left area, convert it to a right area by subtracting from 1. And then you would get that right area as being 0.0401. That means that 4.01% of all men weigh more than 215 pounds. Questions? Yeah. Okay. Next related question. Let's say we wanted to find the probability that a man's weight was between two values. Let's say 215 pounds and 230 pounds. So to recap what we've already done, given a data point, we know how to find the area to the left under the bell curve by finding the z-score and then looking it up in the chart. We know how to find the area to the right by subtracting that left area from 1. But how do we find, so if we were to visualize this, essentially, because we want to find the probability that this variable is between these two numbers, that's the same as finding the area under the bell curve between these two values. So we know how to find a left area, we know how to find a right area. How do we find a middle area in between two values? So you know that we can use the bell curve chart, the z-score chart, to find the area to the left of any z-score. That's what the chart allows us to do. So how do you think we can find a middle area between two values?
Do the problem for 230, do the problem for 215, subtract the difference.
Okay, very good. So we know how to find the area to the left of 230, so this total green area. So find the z-score at 230, look it up in the chart to find this green left area, and then do exactly the same thing. Find the left area for 215, so we would be starting with the green area and removing the red area, in which case we'd get this middle area that we want. So we'd be left with this area here. Okay, so that'll be our game plan. We're gonna find the z-score of both these data points, 230 and 215, find the left areas for both by using the chart, and subtracting those left areas to find this middle area. So 230, let's find the z-score for that. So the z-score for that is the number of standard deviations that 230 is away from the mean. So that'll be 230 minus 180 divided by 20.
2.5.
Okay, 2.5. And once we get a z-score for 2.5, we're going to look it up in the chart.
0.9938.
Okay, so the left area from the chart for data point 230 ends up being 0.9938.
2.5 is 0.9938.
Okay, nice. Okay, everybody comfortable with the chart? Should we project it up again? So if you have your chart, go ahead and try to find 2.5. Go to the first column for 2.5, and there's no second digit here after the decimal, so this would be the same as 2.50. So go to 2.5 and then just go over to the very first column and add an extra 0.00, and that'll give you the left area of 0.993. So that's the left area. Here is 0.9938. And then we want to subtract out the left area of 215, which we actually already calculated in an earlier question. That was 0.9599. And so if we start with 0.9938 and remove an area of 0.9599, we're going to be left with an area of
0.0339.
okay, thanks. So this tells us that that's the probability of having a man's weight that's between 215 and 230 pounds. In other words, there are 3.39% men who weigh between 215 and 230 pounds. Any questions? All right, next related question. So next related question is, let's say that I asked you for the weight of the man that was considered the heaviest 1% of all men. So what is the weight representing the heaviest 1%? So we've been able to make an equivalence between probability and area. So let's visualize this situation. So we look at the weight distribution. We want to find the weight here. That's the heaviest 1%. That means only 1% of all men are heavier than that. That means that this total area under the bell curve is only 1% on the right. So we compare what we've done before, which is I give you a particular number that represents a weight, like 215, and I ask for the probability, which is really asking for the left or right area. In this case, it's basically the opposite, where I give you a left or right area in this case, and then ask for the corresponding weight. So we're going backwards. So let's review how we went forwards to understand how we're going to go backwards. So for the first type of question, question A here, where I gave you a weight of 215 and asked for the probability of being less than that, what were the steps we took in that direction? So here we're given a data point and essentially asked for the left area. So how did we go from data point to left area?
We found the z-score of that data point.
Yeah, so to go from a data point, we found the z-score. That ended up being the second step. And how did we go from the data point to z-score? How did we find that?
Mean minus data point over standard deviation.
Okay, good. Through the z-score formula, or what it needs to be a z-score, definition of z-score. So z-score is data point minus mean over standard deviation. So that's how we went from x to z. And then going from z to left area, how do we find that?
Look up the z-score on the chart.
Yeah, so this is through the z-score chart. And then if we needed to stop at left area, we'd be done, but let's say that we needed to find the right area. How do we go from left area to right area?
1 subtract mean previous number.
Good, so just subtract from 1. So 1 minus left area is the right area. Okay, so that's if we're going in this direction, where we start with data point X, and we need to find a probability or a left area or right area. Then we go through these steps. But in this case, we're given a right area of being 0.01, and we need to find the corresponding value. So we're starting here, 0.01, and starting here as a right area, what would be the corresponding left area?
1.01.
Yeah. So,
Maybe 0.99.
Yeah.
0.99, yeah. So if the right area is 0.01, the left area is 1 minus that, which is 0.99. That's left area, so now working backwards, next step is find the z-score. So we want to go from the left area to the z-score. And remember the way the chart is laid out is first column is z-score, and all the middle numbers represent left areas. Before, we started at the first column representing z-score to find the left area. Now we're going to start in the middle that represents a left area to find the z-score. So let me project that up. So we're looking for a z-score whose left area is 0.99. So remember the z-score table was divided up into negative z-scores and positive z-scores. So how do we know which side to go on?
Because you're on the bigger side right now, and you're looking for the left side, you're gonna be on the positive.
Okay, very good. So we said that a positive z-score means that if you're to the right of the mean, and a negative z-score means that if you're to the left of the mean. So the mean's gonna be here where the peak is. So we're looking for a left area of 0.99. That means that we're more than 50%, which would correspond to the left area of the mean itself. This would be 50%. So because we're 0.99, which is more than 50%, that means we have to be to the right of the mean. And our z-score ends up having to be positive. So we're gonna go to the positive z-score side. And if you didn't realize that, then you could have maybe accidentally gone to the negative z-score side. And when you went to try to search for 0.99 as a left area, you notice you just can't find it. So they go in order. So the smallest left area is 0.0003, and then the biggest left area here will be 0.50, right at where the mean is. So that tells you that if you tried to search for 0.99 on the negative z-score side, you just wouldn't find it. So we're going to go to the positive z-score side. Remember, all these middle numbers here represent the areas. So we're looking for an area of 0.99. And these areas are in order from left to right, going down. So we're going to search for the closest one to 0.99. And you notice that the closest one will be somewhere between 0.9899 and 0.9901, but we're going to pick the one that's closest in distance to 0.99. So the one closest in distance to 0.99 looks like 0.9901. So then we're going to look at which z-score that corresponds to. So that would be 2.3, and then you add on an extra 0.03. So it would be 2.3 plus 0.03, which is 2.33. Any questions? So corresponding to a left area of 0.99, the z-score is 2.33. corresponds to the left area. Okay, so now that we got this z-score, which is 2.33, we want to find the original data point. And between these two steps involved the z-score formula. So we're going to fill in what we know and solve for what we don't know. So in the z-score formula, we know 2.33 for the z-score. And then x is the data point we're trying to find, so we don't know that yet. And then the mean we know to be
180,
180, that's given. And the standard deviation
20.
given is 20. So now all we have to do is solve for x. So this is going to be simple algebra. So 2.33 is equal to x minus 180 over 20. So in algebra, the basic premise is if you start with an equation, a truthful statement, you do the same thing to both sides, step by step, until eventually you isolate just x. And so what might be the next step to do to both sides, to get closer to getting x by itself?
Multiplied by 20.
Yeah, multiply both sides by 20 to get rid of this denominator on the right. So the only thing stopping x from being itself is right now it's being subtracted from 180. So to undo that, you're going to add 180, but you're going to do it to both sides of the equation. So then we get 2.33 times 20 plus 180. So if you evaluate that, that'll be the value for x that represents the heaviest 1%. Any questions?
226.6.
Yeah, so 226.6. So that represents the man's weight that is the heaviest 1%. So this is one way that you could have done it. So I know we're just out of time, but real quick, is one way that we could have done it is just use this formula. Another way that we could have done it is just understand what it means to be a z-score. So we're saying that the data point we want is 2.33 standard deviations away from the mean. So if this mean is at 180, that means we need to move 2.33 standard deviations to the right of the mean to get the data point we want. So that means we're going to start at the mean of 180, and then we're going to add 2.33 standard deviations where there are 20 pounds in each standard deviation. So just multiply by 20. And just by what it means to be a z-score, we get the same answer that we got down here by doing all this algebra. Any questions? Okay, that's it for today, guys. Have a good day.